All right, so just you know, it doesn't have to be pictures. You can write. You don't want to copy the procedure down, because if you copy the procedure down from the lab manual to the book, then there's no point in doing that. What you want to do is you want to make it a lot shorter so you can go through it quickly, because, like I said, speed is going to be a factor as you continue in okay.
Are we going to have a quiz on chapter 24 this week?
This week, yeah. We're going to have a quiz on chapter 24 on Thursday. Since we finished it last week, we'll have it.
Not to this one, do you want also, we're not going to have the 15, chapter 15 questions included in we'll determine our homework?
No chapter 15, just chapter 24 homework, that's it. All right, other questions?
For the lab, do we add the potassium dichromate first or the oxalate?
You would follow the procedure in the book, but that's an interesting question, because you know about adding acids. You AA, add acids. You add acids so that the water acts as a heat quench. For this particular reaction, what do you think? Would you add the more reactive species, or would you add the less reactive species? You know, if you want to control the reaction, what do? You know, do you add, let's say, the more reactive species, let's say you're the, what would an analogy be? Like a piranha or something, piranhas. Those would be the more reactive. And so would you add the cow to the creek full of piranhas, or would you add a piranha one at a time to a cow that's sitting there? Probably an awful analogy, but think about what you would do. Would you add the more reactive, or because obviously you could just read it. You read it and it says, okay, add this to this slowly, right? But then, a lot of people, when it's like cooking. When you cook, do you really think about it, or you just add the ingredients? Some people think about it. Then there's a whole bunch of people who are really into the science of food, and there's a big book. Have you heard? The book is called. I think the book is called The Chemistry of Food, or The Science of Food. I have it. I've read parts of it. It's an interesting reference book to have. But this guy, every year, he gives a talk on ACS. It's the American Chemical Society. They have webinars. And so every year around Thanksgiving, he gives a talk, talks about turkey and about a bunch of other common Thanksgiving meals, and talks about the chemistry of those. Tryptophan and stuff like that.
There was one on the pie crust, and if you mix it up too much, you make a gluten chain. And so you have to just fold it softly, and that prevents that from happening.
From getting all chewy like that. That's interesting. Right. Yeah, he's his name. I can't believe his name slips my mind. But he doesn't have a show. Well, there's a guy on Netflix who's a science guy, but this guy is like one of the pioneers. This book's like 30 years old, but it's like over 1,000 pages long, and so it's pretty interesting about flour and all kinds of gluten and stuff.
What's tryptophan?
Tryptophan? Something. What is it in turkeys, and puts you to sleep basically. That's it. But catch it. The webinars are free to watch if you want to. Just go watch them on ACS. Yeah. Well, anyway, you could. There's a lot of people. There are a lot of people who come into the lab and just cookbook it. Okay, I mix this with that. Mix that with this, right? But in this lab, in Chem 1B, you cannot cookbook it. Because what we're going to do is, after this, we're going to do something called qualitative analysis. I think most of you have done it in Intro Chem. But our qualitative analysis procedure is quite long compared to the Chem 4. And so if you just cookbook it, by the end of the 20th step, you have nothing left, and there's nothing to test, and you get no results, right? And so what you have to do is you have to constantly adjust the quantities that you use, depending on the results you get, because everybody has a different unknown, they're going to get different results. And so this, in that lab, if you don't think about what you're doing and you know how you're doing it, then it doesn't prove very successful. You know, to cookbook it is difficult. They're going to have a cookbook procedure. You know, this is kind of a cookbook. It kind of works, but for some cases, it doesn't work so well. You know, and so you need to know more about the chemistry of what's happening in each particular step. And so, rather than cookbook this, you tell me: do you add the more reactive, or do you add the less reactive? So, the more reactive, the less reactive, the less reactive, the more reactive. What would you do?
Less. Less reactive.
You would add the less reactive to the more reactive. Well, think about AA. AA is you're adding it to water. Are you adding the more reactive to the water or the less reactive? The more reactive. Why? The reason why is so you can control the speed of the reaction, right? If you dump in all the piranhas at once, that's going to cause some trouble. But if you just one piranha at a time, you know, maybe it's a little more under control. That's probably there's something else. What would be a good one? Anyway, that's what I think. You know, when I think about some kind of violently reactive reactant, that's what you think. And so, what are you going to add? Are you going to add the dichromate to the oxalic acid, or the oxalic acid to the dichromate? You know, this is what I mean by, you know, this morning I was listening to the radio coming in, and this guy was saying something about, oh, you know, after the Fukushima, people were after potassium. I'm thinking, potassium? What is this guy talking about? Potassium? Well, you know what he meant was he meant potassium iodide. You know, I was just scanning stations, so I just heard this talk about potassium, so it caught my attention. But they were talking in reference to something else. What were they talking about? Yeah, so he just came out with this. But anyway, getting back to this, you know, so you got to know a little bit about the chemistry, what's going on to do it safely, and then that's one of the things. You know, for example, some people they cookbook it, and so they create huge orange clouds of potassium dichromate. It's happened, and I'm thinking, what is this guy thinking? You know, just blowing up dust of potassium dichromate, inhaling it, exposing everybody else to it. You know. And so I figured, well, it's better, you know, if somebody knows, then they can stop them, you know, saying, you know, you better watch out. You don't want to be breathing this stuff in. But if everybody else is cookbooking it, maybe they're not going to be aware of it. But anyway, going back to this, yeah, you add, which one's more reactive, dichromate or well, this is the reason why I talked about it last week, you know. I talked about which one's much more reactive and which one's...
About water and acid.
Well, I talked about dichromate and I talked about oxalic acid. Which one's more reactive?
Dichromate.
Dichromate is a powerful... Yeah, and oxalic acid is what? Now, of course, I might ask why, you know? Why is dichromate a powerful oxidizer, and why is oxalic acid such a weak, what? Reducer. I said why oxalic acid was such a weak reducer. Does anybody remember that? I said this in reference to... because the numbers, you know, the numbers, anybody can come up with the numbers, right? So if somebody asks you, oh, what's the oxidation state of CO2 plus 2 on carbon, right? Anybody can come up with that number. It's easy because there's a set of rules in chapter 3, you know. What was the set of rules in chapter 3? Assign hydrogen a +1. Assign group 1 +1. Assign oxygen, fluorine, chlorine, iodine a -1. Assign, do you guys remember that set of rules? Anybody can go through that set of rules, right? It's easy. You know, if you follow the set of rules, no mistakes. Simple. The problem is that's all a lot of people can do. You know, when you ask them the extent of the scientific knowledge, well, I can go through that set of rules and I can generate numbers like this. Don't ask me what the numbers mean. I have no clue what the numbers mean, but I can generate them quite easily. Right? Oxygen would go first. There's another set of rules I learned. You know, the set of rules I learned was the most electronegative element gets its normal charge, and then hydrogen's always +1. If it's bonded to an electronegative element, if it's bonded to the less electronegative element, it's a -1. This kind of stuff. You know, there's different sets of rules. The ones in Petrucci work pretty well.
Methane.
Methane, and then actually this is wrong. Made a mistake. What should it be? +4. +4 is significant. You know, in my Chem 4 class, I try to indicate the significance of +4. What is the significance of +4? You know, when we're doing this in chapter 3, long time ago. What is the significance of +4? +4 is important for carbon because it indicates what?
Is that many different bonding sites?
I'm sorry, Ahmed?
There's a lot of different bonding sites.
Bonding sites, it could, yeah, it could indicate. It's, yeah, you know, usually what you try to do is maximize bonding. This is why, you know, carbon would go to +4 to maximize. You know, I could maximize bonding more. You know, the reason why molecules form is to maximize bonding. So there, I just bonded another oxygen, right? And here I'm going to bond another oxygen. Now this is better because I can bond 4 oxygens to stabilize. The more bonds you make, the more stable it becomes. +4 cannot go either way. +4 can only go one way. What way? +4, you know, potentially it could go either way, but there's too much resistance in going one way. You know, this is something I said more than once. Well, anyway, this can only be a oxidizer. Why can it only be an oxidizer? Well, it's electron poor, but there are electron poor species like carbon monoxide that can go either way. This can go either way. This can go both ways. Yeah, something like that. This can only go one way. Somebody frame it. I mean, you use the jargon we used in class about the yeah, it's electron poor, but it's more than that. Because there's another thing you can say about it. And the shell, yeah, you could say it about the shell, but you got to be more specific. What about the shell? For you know, you pre-meds out there, you got to definitely do some more review. So it's more quick because, you know, you have interviews. And I was talking to my friend about the interview, you know, because my friend's an emergency room doctor in Reno, Nevada. And he was telling me that some of the questions they asked him during the interview. You know, one, like, there's it's like a canoe or a boat. The boat can only fit 5 people. There are 7 people on the shore. Something like that. It's a survival situation. Yeah, how do you get them across? It's only one person. You go, yeah.
That's a break you then.
It probably wouldn't get you into medical school, though. But, you know, you think about these things, and so, you know, what do you guys think about? I mean, you know.
What was that answer?
There's no answer to it. It was one of those impossible scenarios. Anyway, Getting back to this, though, some questions should be easy to answer. This should be easy to answer. I mean, you saw it in Chem 1A, and then I did this review. I don't usually spend this much time reviewing, reactions, but a good idea too. And it should be quicker, This is what happens on tests. On tests you're thinking, it just doesn't come to mind. And then you're standing in the Ralph's checkout line and then bing, there it was. Now I remember. But the more the more repeated, you repeat it. Like, I'll tell you, if you read it, let's say if you read it like 10 or 15 times before the test, you would know. It'd be easy. It'd be quick. Speed is critical, right? How do you get speed? You want to finish all the quick questions quickly so you can ponder the more difficult questions on the test. Well, anyway, so oxalic acid definitely is, so we looked at it, right? It was +3. So this is +4 because it's called maximum oxidation state. There's an oxidation state range from minimum oxidation to the maximum. What's the range for carbon? +4 to -4, right? This is -4 at the end of the range. This is +4 at the top of the range. You don't go beyond those, otherwise it becomes too. You can try. Obviously, people try. The people who try to generate exotic species because they want to generate new stuff, right? But this is no normal range, and so like +3 is more on that side, right? Do you guys remember this at all? Me talking about this? Maybe I didn't talk about this. Maybe it could be. My memory's going, like I said. You don't remember, Zach? You remember? Nobody remembers. Okay, maybe I didn't talk to you about this. Well then, remembering back to Chem 1A, which is probably long gone, but you would call this most likely a oxidizer or reducer? Oxidizer. In this reaction, it's reacting with dichromate, which is going to be a oxidizer, right? What was chromium's oxidation state?
+6.
+6 is right. +6. So, this, it could go either way, right? Because it could either lose to +4 or gain, right? But, you'd expect it to gain more because it's somewhat electron, what I call electron poor. But then CO2 is electron poor. This is why I talk about CO2 every semester, because we talk about CO2. CO2 is electron poor, so it's a pretty good oxidizer, right? But why do they use CO2 in fire extinguishers? If CO2 is a good oxidizer and you're spraying, this would be like, oh, you got a fire, you want to put it out. Get a tank of O2. Start spraying O2 on the fire. What do you think is going to happen if you start? Yeah, it's just going to burn more intensely, right? And so the problem is why are we spraying CO2 as a fire extinguisher? CO2 is an oxidizer. It's electron poor, like O2. And so somebody tell me why. Why? The reason is because it's exceptionally weak. Do you think CO2 is a very good oxidizer? No. And so the only thing you have to watch out for CO2 is powerful reducers. Because CO2 is such a weak oxidizer, it'll only react with powerful reducers like magnesium. Did we show the video of magnesium burning in CO2?
It showed sodium being dropped in the water.
Sodium being dropped in the water? Let's check out magnesium burning in dry ice.
Oh, you did.
Did I show that?
No,
Okay. Oh, the break of dry ice? Yeah, so CO2 And so this tells me that oxalic acid should be a better oxidizer or even worse oxidizer than CO2. Tell me. It should be even worse. And so why are we using such a bad reducer? Oh, that's a bad. In fact, this is a worse oxidizer. But you know, as far as reducers go, you know, methane's a good reducer, right? Electron rich. Well, what do you think about this? I would think, you know, even though this is a bad oxidizer, I would think this is even worse, a much worse reducer. And so why are we adding such a bad reducer? Shouldn't we spend a little bit more money and get a better reducer? You know, the oxalic acid is not good for your health either. We could get a better reducer that's less toxic. How about that? Oxalic acid, you don't want to eat this stuff because it's a chelating agent, right? Chelating, you know chelating agents. What are chelating agents? They like to grab ions, right? Oxalic acid likes to grab. You know, oxalate is good ligand. Oxalate's a good ligand because it's a, what do we call it? It's a tetradentate ligand, true? It's got 4 oxygens. There's 4 oxygens can grab onto an ion, bind it.
2 of those are at -1 and 2 of them are at 0. So 2 of them.
Well, technically, we just look at one of the resonance forms. But in reality,
It could be anywhere.
no, all of them are the same. All the oxygens have the exact same charge. All the carbon-oxygen bonds are exactly the same length. You know what the charge on each oxygen is? It's -1/2. The reason why we just look at one Lewis structure is because it's a lot easier to deal with than the hybrid. The hybrid is a little more tricky because when you're thinking about the orbitals involved in this and that kind of stuff, it just, at least right now, let's just look. When you go on to advanced organic chemistry, if you head that way, then you're going to look at MO theory, molecular orbitals, that kind of stuff instead, okay? But for us, we're just going to do the simple valence bond kind of, you know, because when we do this hybrid, you know, what's the hybridization on this? Oh, that's easy. sp3, sp2, 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 right? When you do the resonance hybrid, what's the hybridization on this oxygen? You know, it gets more tricky because you got that lone pair that's floating. You know, remember delocalized versus localized? You got this total delocalization. And so what is it? You know, well, it's probably sp2, sp2 to keep the p lined up like that, right? So both of these go sp2, sp2, not sp3, but that leaves a trick. Well, we got too many electrons. What's going on with electrons? Electrons are going unhybridized p. That actually happened in, I don't know if you had that homework problem. There's a homework problem back in that chapter 10, I think it was. Something like this. You know, here you'd expect this to be sp2 and then this sp3, but it turns out that both of these are sp2. Even though this has 4 groups, it adopts sp2 to throw one of the lone pairs into a p, so we can get some more delocalization of the electron. Although, you know, there's this hybrid stuff. I don't think it was this. I think it was more strictly one which didn't have resonance delocalization. But anyway, this is this Chem 1A stuff, and this Chem 1A stuff is stuff you should repeat. It's not just the stuff that's covered in Chem 1B that you should review continuously going up to the test, but also some of this Chem 1A stuff you should be reviewing continuously as well, so it's fresh in your mind, you know. You can go through this stuff quickly. Anyway, this is a pretty good tetradentate ligand, wasn't it? Yeah? No, it wasn't tetradentate, actually. It's bidentate. So which oxygens, 2 oxygens bind? these two oxygens or these two oxygens, or it doesn't matter. The bottom ones. These ones on the sides cannot bind. Why? Together. They can bind. One of them can bind, but not both at the same time, because
I always think the upper ones are happy with the double bond.
oh, the upper ones are happy with the double bonds? They are happy with the double bonds, but in reality, we know that all of them are the same. That's more, maybe more advanced. Forget, if that's confusing, just know this one. The upper ones would be happy at the double bonds. These ones are going to be more reactive because they give a negative charge. Those bases, you know, electron pair donor, so if you got a negative charge, there's going to be better donor. Why can't these two on the left bind? Somebody explain that to me. This should be quick.
So we're just gonna leave it uneven central out.
No, no. No, wouldn't leave it. It'd be very even. It'd be very nice. It'd look very symmetric. Boom, boom. It's a four-membered ring. Yeah. That's why. Four-membered ring should have a bond angle of 90 degrees. Three-membered rings are even worse because three-membered rings should have a bond angle of 60 degrees. Most three-membered rings species, like epoxides, are explosives. Yeah. They're very unstable. That's the answer I was looking for. That's good. That's quick. Quick recall. Once I was taking this, I was taking this film class, and the professor let us record the lectures. This is like history of French film at UCLA. So I recorded the lecture, and then I was listening to it at night, and I was listening to the lecture, and then I fell asleep. You know, the lecture was running. And the next day, we had the exam, and then just nailed it. You know, everything she asked on the exam, she talked about in the lecture. So it was so easy. But then I was thinking, you know, I didn't even really listen. It was just also, it was weird because, you know, and so that was, but they say, you know, if you can just recall, just remember that information, you should be able to get an A. That's 90% of the test, right? Then 10% challenge problem or something. Sometimes it's like a 25% challenge problem. Most of the Chem 1A exams at UCSB were 4 questions, each worth 25 points. Most of the ones I did. And so there's a very interesting grade distribution that they had.
You were gonna see if you get one wrong.
If you got one wrong, if you left one blank, that's already 75%. Hopefully you got the others all right. Some people there don't believe in partial credit. And so the grade distribution is like 75, 50, 25, 0. It's kind of interesting.
No partial credit?
No partial credit. It's either right or wrong. That's just some people. There are more eccentric people out there, you know, who don't believe in partial credit. Anyway, let's go on here. So we spent a lot of time, wasted a lot of time talking about this because you could just read it. You add the potassium dichromate slowly to the oxalic acid. And you always add the more reactive species so you can easily control it. If the reaction is starting to get out of control, what do? Stop adding it. You know, I told you about that one person who dumped all of it at once. Yeah. It wasn't that violent. It's not like an explosion, but what happened was it just started foaming because it forms a lot of bubbles, you know? It started foaming and splattered all over the place, including their hands and clothes and everything else. You can also wear gloves. You know, I recommend nitrile gloves too. You know, you can buy those at the supermarket, etc.
They have them at the 99-cent store on Manhattan Beach Boulevard, Inglewood Avenue for $1.
Oh yeah. Okay. How many pairs do you?
Pardon?
How many pairs for $1?
One. But, yeah.
One. Oh my. There. You know, They must be very thick.
Yeah,
Oh.
they're almost like they look like a work glove or something.
Oh,
It's
okay.
made with it's very thin against your fingers. It looks
Okay.
like they're working with.
All right.
The black is gray ones.
Okay.
Also, Walmart's got it.
All right, but getting the thick ones, you have to be careful because it depends on what chemicals we're working with. Thicker is definitely better because it's going to offer you more time, so you could reuse them. You can also get the thin ones and just toss them every day. The thin ones are I think I saw like a 6-pack at the 99-cent store, but I'm not sure. Those are
From Walmart for like $8.
$8. Oh, that's a good price.
Because I gotta make the chunky and spill it when they say brand stuff, so I get super cheap.
Oh, Walmart is good because at Costco and Sam's Club, they're already up to $10 for a pack of 100.
Or go to LC.
Yeah. Well, yeah, I recommend the nitrile gloves. Then you don't have to worry so much about contact.
Also got like $1 million.
We have some in the lab. But anyway, if you do spill, just wash it off thoroughly. So those are the types of things you think about when you're going through these. What is the reaction that's occurring? And in fact, one of the good ideas is to try to figure out the reactions that are occurring. In fact, we'll talk about the reactions tomorrow, so you can write those into your book as well. All right, today we're going to continue with the chapter 15 stuff. So did somebody figure out what X is? Who got X? All right, Scott, I'm counting on you. Oh, you didn't finish? All right. Did anybody finish that? Did anybody get X? I should have made it a take-home quiz. Did anybody try? The ice.
Oh, the ice.
For those advanced problems, like I say, like a lot of the tests I took when I was a student were 90% just memory recall, 10% challenge. For those 10% challenge problems, you know what I used to do? I used to, couple of things. One, I used to see what the next class level up was, like the advanced class or the graduate class, and then go to the bookstore and then look at that textbook. And then find, the sections that we were studying, and then look at all the advanced, the sample problems they did there, figured those out, right? And then what I found was a lot of professors, they just took a problem from the next course in the sequence, the higher level course, and then just gave that to the lower level course. So obviously, if you take a higher level course question and give it to the lower level course, this is going to be a challenge problem, right? But if you've seen it before, wow, you have an advantage, right? You had an advantage because you saw it. So that bookstore, library, reference room, do that. Versus, because I like to learn by example, but if I gave you that X, how quickly could you solve for X in a cubic equation like that without a programmable calculator? How quickly? I mean, what would you do? Graph it? How would you solve that, Scott? Huh? Quadratic equation?
You'd have to get an X out of it somehow.
Okay. Would you factor it and get one on one side on the quadratic and then figure out the zero on the other?
Big factor.
Oh, factors?
So, I mean, you can get an X out of it, I think. In the pro.
See, you guys would be competing with somebody like Scott. And how would you do?
Right.
Probably. Or, you know, when you're in a regular class, there are people with all different kinds of backgrounds, you know? Some people. Mhm. Yeah, did you get it?
No, good question.
All right.
What's the difference between aqua and aqua?
Aqua and aquo,
Aqua.
like there's only one. Aqua with an A. There shouldn't be an aquo. No aquo.
For some reason, like on the internet, aqua pops up pretty often.
That's probably a typo.
Okay.
Yeah. All right, maybe I'll make this a quiz. You guys can work on it right now, and then solve some